Hey guys, it's Dr. Wolf explaining homework number 2 for chapter 5. Please bear with me, it's been a while since I've made a video, but here goes. First problem in the homework is number 7, and the purpose here is to look at a medical drug test which is designed to detect steroid use by athletes. So we get this information that the test is accurate 95% of the time. When an athlete has taken steroids, it's 97% accurate when they haven't. Suppose the drug test is going to be used in a population in which 10% have taken steroids. Okay, we're going to make a tree diagram to show a sample space for this chance process. So the first thing that happens in the tree is you have to note in the first sequence of actions whether an athlete either is or is not taking steroids. And we were told 10% were, therefore in the population 90% aren't. Then the second action in the sequence is to test them for steroid use, where it's either going to come up showing steroids or no steroids. And that's considered a positive or a negative result. And in yellow here I highlighted the two probabilities that were given, so of course the other branches in this tree are filled in with the complement rule, so just subtracting the probabilities from 1. So then if you look off to the right, this list of 4 probabilities is all possible outcomes on the tree. Alrighty. The probabilities then were also found just by multiplying the probabilities on the branches. So to answer part B, what is the probability that a randomly selected athlete tests positive? We can see on the tree that a positive result happens here in row 1, and a positive result happens in the third row of the tree. So the chance of positive is simply found by adding those two numbers to get 0.122. Part C, suppose that an athlete tests positive. What's the probability that he or she actually used steroids? So now in part C, it's super important to realize that that was a conditional probability question. Suppose the athlete tests positive. That's your given condition. Find the probability that they actually are steroid users. So in the conditional probability formula, we taught you the other day to put the intersection of the two over the given. So steroids and positive, that numerator comes from multiplying the top set of branches, and the denominator, P positive, comes from the answer we just got in part B. So we take those two and divide, and we have a 0.7787. Now that's supposed to be a surprising result to you. Even though the test sounds like it's 95% accurate and 97% accurate, when we give you the idea that an athlete has tested positive, the chance that they actually are steroid users is only 77%. So that should be surprising, and that is true for many, many, many medical testing devices. And that's often the reason why there is a second opinion and the test is done twice. Okay, next problem about Mike's Pizza. You've got information about 7 pizzas in the oven. 3 of 7 have thick crust. One of these, 1 has sausage, 2 have mushroom only, the remaining 4 have regular crust, blah, blah, blah. Choose a pizza at random from the oven. Part A, are the events thick crust pizza and getting mushrooms independent? So guys, I used T and M to label these events, and remember what we have to do to check for independence. We have to check if the probability of T given M equals the probability of T. So I drew out the oven. I drew out the oven to help us answer part A. The probability of T given M. How am I going to do this? Well, given that 4 of the pizzas have mushroom on them in this oven, the chance that they are thick crust is 2 in 4. One can see that right from the picture I drew of the oven. If you wish to use a conditional probability formula, you can break this into T intersection M over M, and then the numerator of T intersection M is 2 pizzas in total in the oven. 2 out of 7 are thick crust and mushroom. That'd be these 2. 4 out of the 7 pizzas in the oven are mushroom. Dividing those two fractions, we get 2 out of 4. Now we must also separately get the probability of thick crust. Well, clearly in our oven, 3 out of the 7 are thick crust. So we say since 2 over 4 doesn't equal 3 out of 7, events T and M are not independent. For part B, We now add an 8th pizza to the oven, and the 8th pizza is thick crust with cheese only. So I added the 8th pizza. Now are these events independent? Well, now if I do T given M, given that the pizza has mushrooms, the chance that its thick crust is now 2 and 8. The chance of thick crust by itself is 4 and 8. Since 2 out of 4 equals 4 out of 8, we now would have the events T and M independent. Number 9, we get this two-way table showing us that deer will eat almost anything green. In a study of pine seedlings at the Environmental Center in Ohio, researchers noticed how deer damage varied and how much the seedling was covered with thorny undergrowth. So thorny cover, yes or no? And, deer damage, yes or no? Thorny cover, basically broken down into none, less than a third to 2/3, and greater than 2/3. Well, as you know, you guys, you have to put the totals into the two-way table so that you can answer these what is the probability questions. So what is the probability of a randomly selecting a seedling that was damaged by the deer? That'd be this number, 209 out of 871, changed to the decimal point 24. Part B, what's the conditional probability that a randomly selected seedling was damaged for each given level of cover? So given the level no cover, damage is 0.2844. Hopefully you're showing me fractions first, decimal second. Given that the coverage is less than a third, the chance of damage is 0.3248. And given that the damage was 1/3 to 2/3, etc., there are 4 conditional probabilities to calculate. Part C, does knowing the amount of thorny cover on a seedling change the probability of deer damage? Well, yes, clearly knowing the amount of cover does change the probability of deer damage. It appears, based on the probabilities we just calculated, that deer do much more damage when there's no cover or less than 1/3 cover, and much less damage when there's more cover than that. And those 4 probabilities right here would be the justification for that. Okay, number 10, random walk on Wall Street. So this random walk, blah, 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 you get the probability that your portfolio goes up in price is 0.65 in any 1 year. And then you're willing to assume that this probability is correct for a portfolio containing equal dollar amounts of all common stocks listed on the New York Stock Exchange. What's the probability that our portfolio goes up for 3 consecutive years? So guys, as long as we're presuming that up, up, up for 3 consecutive years represents independent events, we can simply take 0.65 to the 3rd power and simplify that to 0.274. And then what's the probability that the value moves in the same direction, either up or down? Okay, notice the presence of the word or. So if we go up 3 years in a row or down 3 years in a row, we are going to add for that or. Then we have 0.65 cubed for up, up, up. We have 0.35 cubed for down, down, down. And the sum of those is 0.3175. All right, last problem, number 5. So we have information about a child getting a certain blood type based on genetics. So let's see. Part A, Hannah and Jacob both have alleles A and B. Diagram the sample space that shows the alleles that their next child could receive. Then give the blood types that the child could have along with the probability of each one. Okay, so a child. To have A from mother, B from mother. There's those probabilities based on the information above. And then they have to get either A or B from father. So all the possible outcomes are going to result in either the 2 kids having both B, one B and not the other, not B with B, or both not B. So when we do these 2 kids, that's what's shown on the sample space. Because these were all probability 0.5, we have a 0.25 probability for each outcome. So the child ending up is either blood type A, AB, or B is these. Okay, I think I was ahead of myself. Part B, Jennifer has alleles A and O. Jose has alleles A and B. they have 2 kids. What's the probability that at least one of them has blood type B? All right, so then the 2 kids are, all possibilities are right here. Here's the tree diagram in the second scenario. So the resulting blood types are either going to be A, B, A, or just B. And at least one kid is B. That's 3 of the outcomes. So we go back to the tree and we multiply the branches and add them up. Or there's another important way to get the probability of at least 1, and it's 1 minus the probability of none. So you could do 1 minus the product 0.75 times 0.75 to get the 0.4375. So that ends problems. Here are the multiple choice. You can see that I showed my work here to come up with the probability that neither test is positive. So neither test is positive in all of the outcomes in the sample space. It's just this bottom row. I'm doing a lot of unnecessary work just to explain that whenever we do a test, we can come up with test A, test B being both positive, positive, negative, negative, positive, negative, negative, and I just figured out all of the outcomes in the sample space to give a complete answer here, but we were only interested in this one. Next multiple choice. When I read a paragraph like this and I see something about a sequence of events, first whether or not a person has food poisoning, and then whether or not they attended the party. So when you look at the probabilities that are described in the paragraph and you translate them to the tree and you're focusing on this number right here, this 0.40, you have to understand that this second tree branch right here, following the first tree branch, is a conditional probability of attending the party given that you got the food poisoning. So if 0.40 is the probability of A given F, none of those are listed here. So go back and read this problem carefully. Carefully fill out this tree and understand that when you write these 4 numbers on the second set of branches, those are conditional probabilities, none of which match the choices. Loaded die. So this loaded die idea is the idea that one of the faces, one or more faces of the numbers 1 to 6 are not going to have the same probability as the other face. That's what we mean by a loaded die. So if this die is thrown and the top face shows an odd number, what is the probability that the die shows a 1? Again, you have to realize that that's a conditional statement. If the die shows odd, what's the chance it's a 1? Break that down into probability of 1 and odd over odd. So you have 1 and odd is 0.3, and then odd is these 3 added up, so you have 0.5 in the denominator, simplifying to 0.6. Okay, then we get just into these review exercises, and I think since this video is already long, that I'm not going to explain the review exercises. So that's it for the Homework 2 review video, and hope this helped.